Now, I'm a big tea drinker, and I usually like to have a little sugar in my tea. Now, what I'm going to show you is something that I'm sure you've seen before. When I put the sugar in the tea, initially the sugar drops to the bottom, but very quickly, as I start to stir, the sugar seemingly disappears. I end up with a very clear, transparent solution, as if the sugar never was added. Now, we know that the sugar is there. Our taste buds tell us the sugar is there. But where did it go? Why don't we see it anymore? What I've just prepared is an example of a solution. A solution, in chemist terms, is composed of a solvent, in this case the water, or the tea, but really the water, and the solute, in this case being the sugar. The solute, again, being the thing that we add to the solvent to make a solution. Now, solutions can be solids added to liquids, but they also can be liquids added to liquids. For example, let's go ahead and take some water. Again, very common experience for you, I'm sure. We'll add a little bit of alcohol. And once again, if you notice carefully, I have a uniform solution, completely clear, transparent. Seemingly, the alcohol has disappeared, or it has been mixed into the solvent in this case, giving us, again, a solution. Now, here's a question for you. So in this case, we would call the water, again, the solvent, and the alcohol would be the solute. But what if I instead were to use the alcohol as a solvent? And to the alcohol, we'll add a small amount of water. Once again, we'll stir it up. Once again, we get a solution. So notice that in this case, the alcohol was indeed the solvent. The water now becomes the solute. So one thing we learn is that solute and solvent are relative terms. The solvent referring to the material that's in the majority, the solute referring to the material that's in the minority. Now, in addition, we can have gases dissolved in liquids. That's an example of a solution. Carbonated water is a good example of that. We can have solids dissolved in other solids even. You have to think a little bit harder to find examples of that, but in my head, in my teeth, more correctly, is an example of that. That's an example of mercury mixed with silver, making a solution, fortunately a solid solution so that it stays in my teeth. So we understand then what a solution is. Let's start to understand, again, back to the question of where the sugar goes. Why don't we see it? To understand that, we have to go to the molecular level. And so let's represent the sugar crystals as this chunk of Lego blocks here. And when it's dissolved, and we'll get some water molecules here to help us out. And again, if you can imagine being at a molecular level, as soon as the sugar is dissolved, the individual molecules of sugar are broken up into individual molecules and surrounded by solvent, again in this case water. And the result is that in the solution there are no particles that are sufficiently large anymore to scatter light. In other words, we do not perceive any cloudiness or anything. The solution appears clear. We don't detect by our eyes the sugar particles simply because they are so small now that we don't see that. Now consider, for instance, something else very much related. Let's go back to our tea for a moment. This time we'll add a little bit of milk, something else I like to have in my tea. Once again, we'll stir it around, and there's no surprise to you. I can stir this all day, and I'm not going to get a solution. I get something different now. I get something that remains cloudy throughout the day. This is something we would refer to as a suspension. Again, so this is an example of what a solution is not. Both a solution and a suspension are mixtures, simply mixtures of materials, but the difference is a suspension appears cloudy to us. So again, let's go to the molecular level and try to understand what's happening in the molecular case. And in fact, let's show you a picture here. In the molecular case, at a molecular level rather, a suspension simply means that particles are still of sufficient size that light can be scattered off them and we see them by our eyes. So I show you all three types of a mixture that we could have here. Represented down at the bottom would be representative of a sugar crystal sitting on the bottom of the tea before we mixed it. It's a solid and it's sufficiently large that gravity pulls it down to the bottom. The next kind of level would be a suspension where we now have particles that are small enough that they're not pulled down by gravity. They stay in solution, but they are large enough that they reflect light. They scatter light so that we see this cloudy effect. And then in the limiting case, the particles are sufficiently small that they can't scatter a significant amount of light, and it appears colorless. It appears to not be there because, again, the particle size is very small. Now, there's one other property of solutions that we want to address here, and that in particular is important when we're talking about aqueous solutions. Solutions, again, made up with water as a solvent. That's not a solution, remember that. Where's my, with water as a solvent, there we go. Okay, and this has to do with conductivity of electrical current. Now, let's go ahead and if we zoom our camera back a little bit, I have a setup here consisting of a light bulb that is plugged into the wall. But the light bulb is not lighting up simply because there's a break in the circuit right now. These two wires, if they were connected, would light up the light bulb, but right now they are not connected. They're just going into this beaker and not touching each other. I'm now going to take some water and I'm going to pour it in. Such that it's making contact with the wires. I observe that there is still not sufficient current through this cycle to light the light bulb. But now watch what happens when I add salt. Pretty amazing, huh? So something's going on. When we make a solution involving salt, the light bulb lights up. That tells us that the solution is capable of conducting electricity through this circuit. Now I want to compare that observation with a second experiment. Once again, let's go back to, and I have an identical setup here. You have to trust me on this. It's exactly the same as before. I'll add water. This time we'll add sugar. And I can add sugar and add sugar and add sugar, and the light bulb will not light. So again, we see a fundamental difference. Both of these eventually would be solutions, the salt solution and the sugar solution. Yet, even though they both are solutions, the sugar fails to conduct enough electricity to light the light bulb. In fact, very little electrical current is going through this circuit. So again, we need to look at the molecular level to understand the difference between these two solutions. So let's go to a blank paper. This time I'm going to represent sugar with, again, I'm going to represent the salt now with Lego blocks. And the fundamental difference, so again, we'll bring in our water molecules here. The fundamental difference, as we're going to see, is when the salt dissolves, it doesn't dissolve as sodium chloride, NaCl, but it would dissolve as individual sodium and chloride ions. In other words, water has a rather unique ability to separate these charged ions. The sodium ions being positively charged, as we'll see a little bit later, well, I will get into that next. But the charged particles for both the sodium and the chloride are separated by the water molecules, and as a result, we have In solution now, in contrast to the sugar, we have charged particles, and those charged particles are capable of facilitating transfer of electrons through the solution, thereby lighting the electric light. So again, the difference between a salt solution and a sugar solution is that the salt is capable of being dissolved into charged particles, whereas the sugar is not. It stays as neutral molecules. We refer to the salt solution as an electrolyte, meaning it conducts electricity. The sugar solution is a non-electrolyte, meaning it doesn't conduct electricity. So summarizing then, we've learned that a solution is composed of a solute dissolved in a solvent. We've learned that a solution is not a suspension. A solution, one of its fundamental properties is, if it's a solution of a solid in a liquid, is that it's transparent. We've learned that solutions can come in two forms. They can be electrolytes or non-electrolytes, and that depends on their ability to conduct electricity.